Okay, so let's check for question 2. Okay, while waiting for Daniel. Okay, so question 2 is figure Q2A shows a circuit to generate AM modulation signal. Okay, at a transmitter. So a modulating signal VMT is in the form of cosine wave. Okay, so we have learned this yesterday. If you not done it, please at least you try to respond to me in WebEx chat. Okay, so given that radiant frequency of local oscillator that is used to generate the carrier wave is 20,000 pi. Okay, this one is radiant frequency, means omega. Okay, omega 20,000. If the required 20,000. Why is this 15,000? It's okay lah. As long as you understand the concept. I don't know. There is type, maybe during this exam they already mentioned it's a typo. Because here is 15,000, here is 20,000. But it's okay. I just want to check the concept. The required modulation index of the AM signal is 0.25. Mean you have the ratio 0.25. EM over EC equals to 0.25. Determine the amplitude of the carrier signal. Okay. So this is pretty much straightforward. So you have M equals to EM over EC. So M equals to 0.25 equals to EM over EC. So EM, you know it too. Okay. Okay. This is pretty much easy for the 1A. That's why it's only 2 marks. So we have M. Is it recording? Okay, we have M equals to 0.25, it's given. Okay, and M we know is actually a ratio of EM over EC. Okay, so EM is given as 2 volts. Okay, 2 volts. So you can know what is EC actually. What is EC? Can you guys calculate? What is the amplitude of the carrier signal? What is the EC? Respond at WebEx chat. At least you try now. Although I spoon feed you how to do it, you won't have like this in the real test, right? But at least you do the calculation for me lah. Okay. So what is the answer? What is the amplitude of the carrier? So the amplitude is 8. So this is amplitude. Next, determine the complete mathematical expression of the signal at point A and point B. Okay, before we start that, okay, don't refer to the slide. Okay, close your slide. Don't refer to your slide because I want to test your memory now. Now, you see this? What kind of generation of AM modulation here? Is it double sideband full carrier? Double sideband suppressed carrier? Double sideband, single sideband suppressed carrier? What kind of AM modulation is we are trying to generate here with this kind of system? Is it double sideband full carrier, double sideband suppressed carrier, or what types? Okay, can you answer your question? This is important, okay? I mean, like I told you. Okay. So Hanisa say DSB FC. How about the rest? Sepatutnya dalam buku ada. Ada kan dalam buku. Tak, no, don't. For you, don't open your book. Please imagine this is the real test. Do you able to distinguish whether this one is which one? Okay, so it is actually DSB FC. Okay, DSB FC because we have the component carrier. We have the carrier that should be mixed added together. Okay, if we want to have double sideband suppressed carrier, okay, double sideband suppressed carrier, we don't have anything to be added here. Totally zero here, no connection. So for double sideband suppressed carrier, we only have VMT and we have omega C. Then we mix them then just go here directly. Okay, this one is for EC. This one is for EC component, the carrier component. In our envelope equation. Okay, so we have this. We have this EC. Okay, so if we don't have this, we don't have carrier. Okay, so it will be double sideband suppressed carrier. Okay. Salah tu non Nadira. Okay. This one is double sideband full carrier. Okay. Okay, determine the complete mathematical expression of the signal at point A and point B. Hanisa, you dah buat ke ni? 2A2? You buat yang bawah
Saya buat tu.
You buat
Ada point A, point B.
Mana jawapan dia?
Jawapan dia tu yang tulisan warna merah, point A.
Apa suara you macam cakap dalam air Kejap.
Mikrofon jauh kot.
Tak ada pun jawapan. You dah buat ke? Ni
Dia dah jawapan ni. Tu.
Okay. So this is the answer. Okay, let we see how she do it. Okay, like I told you, there is some error with the question. I don't know why they mentioned here carrier is 220,000 pi, but here is 15,000. But it's okay. The main thing is that you know this is carrier, then this to be mixed. Okay, so determine the complete mathematical expression of the signal at point A here. So this one is what happened is actually VMT time with the carrier signal. So EM cos omega C, 2 cos, okay. Even the radio frequency also local is a generic 30,000. Signal period. Signal period here 1 millisecond. So 1 millisecond, you should able to know what is the frequency lah. Frequency modulation for the modulating signal is F equals to 1 over 1 millisecond. So Hanisa, you do it from here, right? For the omega M. You take it from here, right?
Doktor.
Okay, 2 cos 15,000. Yes, you take here. This one is wrong. Typo. Okay, so 2 cos. Okay, so the concept by concept is correct. Okay, the way she do it. But the answer, I not check it because I don't have the answer, but it's correct. Okay, the way she do it. As long as this one is correct. This one she derived from this one. Okay, so which is correct. Okay, then we go to the next one. Good. And then point B. So point B is actually full modulation. So full modulation. So you should have this envelope equation. And with the and multiply with the carrier component. Cos omega C. Mana? This one Okay. EC cos omega CT. EC. Correct. The working is correct lah. EC cos omega CT plus VMT cos omega CT. So 6 marks lah. Correct lah. Tapi I mean in terms of working is correct lah. Okay. Then we go to the next one. B you dah buat juga tak? Have you done for B?
Tu.
Okay, so B is AM demodulation now. Okay, just now is transmitting. The question is about transmitting. Okay, and then the next one is about receiving. Okay, so just like your test one is complete, you will have all the chapter covered. Okay. Okay, so Daniel have shared number 1, but we will discuss that later. We go through number 2, since we are in progress of discussing number 2. Okay, number 2, AM demodulation circuit. Okay, so what is the other name? Don't check. Don't see your Webex chat. Don't open your slide. Don't open your book. Okay, what is the other name? 2 names of demodulation circuit for the full AM. What is the other different name? 2 names. Don't open your book. Don't open your slide because imagine this is the real test. What is the other name for demodulator circuit for the double sideband full carrier? Don't open your book. Don't open your slide. Try to answer. Because the last time we already told you, right? What is the other 2 names? names because I want to test you, because if the question, for example, in the final, if they use different term, then if you don't know what is that term, then you cannot answer. So what is the other two names of the demodulation circuits? Okay. Correct, detector circuit. Other names? Yes. Okay, rectifier is not that correct, but is near to correct. It is diode. Okay, it's a diode detector. Okay, because diode is actually serve as the rectifier lah. Daniel, don't worry if you just now you have internet
Brother,
problem.
saya upload kat Telegram.
Okay, okay. Jangan risau,
Yeah.
I share it. I record this so you can see where you miss tadi lah. Okay.
Yeah.
Okay, so this is a AM demodulation circuit at the receiving part. So the other name for AM demodulation for full AM is diode detector or detector circuits okay, or detector circuit we can call it detection circuit, detector circuit, the same thing okay. So receive AM signal is shown in figure 2B. So this is your 2B. Okay, this is your receive AM signal. Okay, so you can see this is actually EC plus EM. This one is minus EC minus in bracket EC plus EM lah. Okay, so the AM signal is shown in figure Q2B1 received at the receiver and used as the input of the demodulation circuits. Okay, just like I told you. Okay, so let's say we have antenna here at the receiver part. Okay, so we will be receiving the modulated signal. Then we have the demodulation circuits. Okay, one of them lah, the demodulation circuits. So demodulation circuit is that we try to retrieve back the original signal, the information signal, maybe not similar in terms of scaling, in terms of amplitude, because like I told you, the receive signal usually weak, okay, will not be the same strength as what we transmit. Okay, it's normal because it further travel distance and then distorted by noise. But at least we try to retrieve in terms of the information, in terms of the shape. Okay, we try as much as possible to retrieve that. Okay, so that is the role of demodulated circuits. Okay, so discuss two advantage of AM demodulation. Like I told you yesterday, okay, full AM, even though double sideband full AM is not really it has its own disadvantage. Advantage, disadvantage, but it has on pronounced significant disadvantage at generating side, because we submit carrier as well. Carrier didn't have information but it's wasting of energy, and we submit both sideband. Both sideband knowing that both sideband actually containing duplicated information. However, the advantage of AM actually at the receiver part. Why is this AM full AM is actually more better than the other methods. Okay, even though the other method is saving energy, we don't waste power, we actually transmit only one sideband, okay, for example, instead of two. So the advantage is coming from the full AM is on the demodulation part. Okay. Discuss two advantage of the AM demodulation circuit as shown in this one. So what is the advantage? Can you guys tell me? The vibration, of course, Hanisa have her answer. Okay. Oh, cost efficient simple. Okay. I ask you, then I open this one, right? Okay. Never mind. Okay, so the cost, you see, this is simple circuits. Okay, simple circuit, you just have to use this. And then it is simple implementation. You see, there is actually only this. So, if you see from the circuit itself, in terms of generation, you see double sideband full carrier. Even in the generation part is quite easy compared to the other circuits. But the advantage of full AM is coming. I mean, the more advantage is coming on the receiver side. Okay, because of this circuit lah. Okay, this is easy. Okay, cost efficient, simple implementation means it's not complex lah. Okay, so from the AM demodulation circuit in figure Q2B2, state the name and describe the function of block A, block B, block C. So if you see, this one is actually what you learn in electronic device. So it is a rectifier, means and it is a half wave rectifier. What does it mean? Means half wave means we only allow either the first positive, either we allow the positive cycle or we allow the negative cycle. Let's say the question, I don't know the question, right? Let's say the question reverse this. For example, you should know what the function is still the same. It allows the second half of the complete cycle. However, it will allow the negative cycle if it's reverse bias. Not right. Okay. So it depends, but the function is still the same. Okay. So it's a half rectifier, not a full rectifier. Full rectifier means you're going to have the full cycle. Okay. So block B, what is the function block B? Block B is actually the low pass filter. Okay, low pass filter where we actually filter out the carrier. We only take the information signal, which is also known as modulating signal or message signal or baseband signal. Okay, so we only low pass filter is for us to filter out the carrier because carrier is higher frequency, right? So that's why we use low pass filter. We want to filter out the carrier, and what we left from there is only the signal with the only the low frequency signal with the DC part. Okay, from here with the DC part. The DC part contributed by the EC, by the magnitude of ECU. Okay. You'll is my okay. So you have EC, the full AM signal EC plus a VM, and cos omega CT. Okay. This one actually you can see from, okay, so this one is the one that you receive lah, the one that you receive. After that is the signal pass through the diodes. Okay, pass through diode means it is rectified. Means you only receive, the signal will be, original is like this. Okay, full AM. Then when it pass through the rectifier, which is this one, okay, so we only have the first one. Okay, we only have the first positive cycle lah. Okay, and this one is, you need to check for the tau. Okay, tau equals to RC lah. Okay, you need to check or you don't need to check, it depend on the question but you should know what is tau RC. If it's too small, why, what is this impact? If it's too high, what is the impact? Okay, so then it will, after that it will pass through the low pass filter. Then what happened to low pass filter? We filter out the high frequency. Okay, we filter out this. Okay, so we pretty much left with EC plus VM. Okay, don't forget we have diode switching function. Okay, so we have diode switching function. So here we already start to have diode switching function, which is K. Okay, then when it goes to the low pass filter, the output from the low pass filter, you're going to have EC plus VM as well, and don't forget with your KT, which is your diode switching function. Depends on what okay, depends on the function. If there is any, it will be given. If not, we assume KT lah. Okay, we assume KT lah. So pretty much if you see, this is actually a DC component and only the lower frequency signal, okay, which is our modulating signal. Carrier is already filtered up. Okay, so because it is a modulating signal with DC, so it is actually shifted up. Okay, shifted up by a DC value lah. Okay? By a DC value and also this one. Depends what is this so it be shifted up, and after that you will have, after the signal pass through here, it will pass through the next stage is a DC blocker. So what a DC blocker did is that it will remove the DC component, only retaining the one with the alternating current. Okay, so in the end you will able to get, okay, this one is the from the after low pass filter, this one is after DC blocker, so you receive your original signal again lah, although it can be small, but at least it is the same signal that we are trying to submit. Okay, maybe for example only analogy, maybe we try to submit with 10 volts, the one that we transmit, the one that we intend to transmit, the modulating signal before modulation, of course. But then when we do the demodulation, and then it pass through diode, it pass through low pass filter, it pass through DC blocker, then we maybe only have 0.1, for example 0.1, but at least it is the same signal, because even though it is weak signal, but it's the same signal, later on you just need to amplify. Okay, amplify is easy, right? Just amplify, then you can get back the signal being strengthened back in terms of amplitude. Okay, remove DC parts. So then we see the signals. Okay, so block A, yes, block A is this. Anissa is correct. So block A is this. So you have a ripple here. It's not actually a ripple. This is actually the modulated signal. Okay, modulated signal creating this ripple, look like ripple, this one, because this is actually modulated signal. We have carrier, okay, carrier, and we have amplitude. What is amplitude modulation? Amplitude modulation is we change the amplitude of the carrier. We change the amplitude of the carrier following the amplitude of the modulating signal. That's why it called AM modulation. Frequency modulation, we try to change the frequency or phase of the carrier following the modulating signal. So it's different. Okay, let me put in terms of words. Do you guys need this? I just not sure you guys need this, but I just take it. I just put in our Telegram, because if I delete it, then it's finished. But not sure. Okay, put here. Okay, so just a recap no, the concept okay, I don't know whether you AM is actually okay, AM. So FC we will study later in the next chapter. Okay, FC pula FM. So AM modulation is where our frequency, our carrier is actually change its amplitude amplitude carrier. Okay, this I just for you to understand, amplitude carrier following our modulating signal. Okay, which is our message signal. For the FM modulation, it is either phase, it's either frequency or it is phase. Okay, following the modulating signal. Okay, so like we have cos, okay, cos omega CT plus T, right? Never mind, phase shift. Okay, phase shift. If you see, if we change the focus, if there is changes in the frequency, it's still inside here. Okay, so that's why frequency modulation, we call it angle modulation, because whatever changes, okay, in terms of the phase or in terms of the frequency, it will impact the entire angle, right? Because it's cos theta. I mean, this is a cos angle, so that's why I call it angle modulation. Okay, so frequency modulation can be recognized by two, whether it is angle modulation means the entire, or phase modulation. Phase modulation means only this one. Okay, so I just put inside of Telegram. If you don't need it, you can delete it. Okay. 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 So that is the things. Okay. So this one is actually your modulated signal, but being rectified. So we only take the positive half. But if it's reverse bias, no problem. Then we take the lower part. But you need to understand the concept. Okay. So this is correct, and this is this will involve the tau. Tau equals to RC value, the one with the rectified. Tau equals to RC value. Cannot be too small and cannot be too big. Okay. So if you tau is I'm not sure if it's is it given in the question. I mean, is it given in the appendix? I think no. If not, you need to actually memorize okay. What is the tau minus what? Okay. So you RC it should be 1 minus m square over half. Okay, it seems long, right? And this one is not covered in your appendix, And actually, the this is the complete one, but we can approximate. Approximate to what? If you cannot if you cannot remember this, at least you remember this one. This one is very easy. 1 over what? Can you tell me? 1 over what in the Weber's chat? Because it's important. Let's say we ask, and this one is not in the appendix. This is time constant, RC. Okay, this is of course long if you want to memorize. This one is the shorter one, but it is approximate, not entirely equal. So what is it? Can you tell me in Weber's chat? It is not in the book, but it is in the slide. The book tak ada. The book tak ada. The book only have this one. Complete what? But it doesn't have the approximation. So can you tell me what is the approximation? Slide. Yes. So it is 1 over omega m. So at least if you, for example, if you think that it is difficult to memorize this, okay, because it's too long, right? So at least you're able to know RC is approximation of 1 over omega m. We never know what is will be in your final because final we don't have yet your final exam. But that's why we just need to be prepared because question can be anything Okay, final is even more tricky Okay, so this is 1 over omega m approximation if you unable to remember equals to tau Okay, time constant. Okay, so that is it, and we cannot have too small ripple. So if okay, now close your book, close your slide. What if we have if the time constant is too small, what will happen? If time constant is too small, what happen if time constant is too small? Yes, the capacitor will discharge too fast, correct? That is the process. Good. What happened after that? Good as Zenhua, What happened after that? This is good also. When it's discharged too fast, what happened? What happened to the this one? The shape, Okay, so it's not actually okay. I mean, okay, it's like sawtooth, huh? Okay, means correct as well. So, but the real one is that when you have if the capacitor discharge too fast, it will look like sawtooth. Means it will have more ripple. Okay, we don't want to have it more ripple look like shape, huh? Because we want to, if possible, to have it smooth lah. Smooth, for example, almost like this lah. Of course, this one is after filter lah. After filter, we want it to have like even it's ripple, but ripple constitute to smooth transition process, huh? Transition curve shape. Okay, so if you have the discharge too fast, then you tau equals to RC, time constant too small, you have more ripple lah. Okay, so the signal not distorted, it's not distorted. Okay, so if we have the, in contrary, if we have signal which is if the tau time constant is too big, okay, then you have diagonal clipping. Diagonal clipping means I think you learn in diagonal clipping one, in your electronic device, because instead of having more ripple, it is on the opposite side. Okay, it will have diagonal clipping. Okay, if we have time constant is too big, so you cannot have time constant too big or too small lah. Okay, so this is block B. After the low pass filter, you see we end up with having the signal of almost similar to our modulating signal, but with a shift in DC, because we just filter out the higher frequency, which is carrier, but we didn't filter out everything, so we still have the information signal with DC. Then it go here, DC blocker. Okay, what DC blocker did is actually remove the DC parts, then retain only the AC part. Okay, so which is this? So it's correct, so let's say if we ask you, if we give you equation, for example, you should be able to know how to, not only to sketch, but also know how to show the equation. What is the equation for this stage? What is the equation for this stage? For what is the equation is this stage? This is a good past test where you actually able to test yourself. And this is only the full AM. Okay. So of course full AM is the basic. You need to master full AM first. Then you can do, then you can do or learn the other generation of AM and detection of AM, which is double sideband suppressed carrier, single sideband suppressed carrier, and vertical sideband. Okay, so with that we finish. Okay, no, we finish, is it? Not yet. Okay, so we discuss on sorry, Daniel. If you want to go to next class, okay, because I only have 5 minutes, but I want to discuss. Mana jawapan Daniel ni?
Saya upload kat Padlet.
Oh, Padlet. Okay.
Upload kat Padlet dah.
Okay.
Okay.
Okay, so here question number 1. Okay, number 1A is you just follow the 1A is can be anything. That's why when you read the slide, make sure you understand. For example, we will ask you, for example, what is the trade-off of modulation? So one of them is maybe like if we want to increase the bandwidth, what we want, if we increase bandwidth, what is the benefit, but what is the disadvantage? So this question, technology and physical problem are among main obstacle in designing and efficient. Discuss two issues related to technological problem. This one you can actually Google, but actually hopefully you're able to understand from the slide, because this question, even though it's bonus mark, but it can be anything. Okay, so next we go to this. Johnson noise was first measured by Johnson B, whatever it is. He has proven that generated noise power is proportional to temperature and bandwidth, which is Pn equals to kTB. So Johnson noise is actually also thermal noise. Thermal noise because it is coming from temperature. It caused by temperature. When temperature is increased, the activity of electron is becoming more aggressive. So when activity of electron becoming more aggressive, so there is undesired flow of electron, because we give them, due to temperature, it's heated up, so the electron is more is aggressive than what we expect, and it's not the normal. Then that's why we have this noise. Okay, noise generated by because of the temperature. Because when there is a flow or movement of electron, means there is a movement of current. Okay, so this current can be undesired because it's generated by the by the temperature. Okay, indirectly lah. Okay, so that's why temperature is the main cause, but it's the process. You should know what is the process. So one measured of M with frequency range, this one. So this is the bandwidth and has input of 75. Okay, calculate noise power in watts. So this is actually BN. Ini je ke mana jawapan ni?
Saya buat yang tu setakat tu.
Oh, ini je.
Ah.
Okay. So this one is calculate noise power in watts. Actually this pretty much direct. Pn equals to K given T given this one, but you need to convert to Kelvin. Convert to Kelvin, and bandwidth is given. Bandwidth is 7.5 minus 500. Okay, so this is the bandwidth. Okay, bandwidth. And after, which is 7 megahertz. Okay, so you can know the answer directly. So, and then dBm is, you just need to change it to dB. You log whatever answer that you have in the linear, and log the answer, log in bracket. Okay, so the first answer, the first one is Pn KTB. Pn. Okay, whatever you get KTB. Right? You get X. Okay, value, watt. Okay, so this one is 70 degrees Celsius, but you need to convert it to Kelvin. What you get. This one is the bandwidth, which is 7 megahertz. Then P, in terms of dBm, it's just actually 10 log X over 1 milli. Okay, so this answer will give you BM. Okay, so
Saya
next.
rasa saya terskip satu step tu.
Tak apa. So this one is actually noise power. Okay, noise power caused by the temperature. Okay, the noise power can be modeled using Thevenin equivalent circuit. Using this circuit, show how the noise power can be related with. This one is you refer to the slide. There is slide right on this. Refer to slide and the module Okay, so the Thevenin equivalent. Okay, then calculate noise voltage of the amplifier. Noise voltage of the amplifier.
Yang saya buat ni saya rasa untuk nombor 3.
VN. Can you explain what is this? 138
Yang tu yang apa, Bowman constant. Apa nama dia?
KTB.
Yang 4K TBR.
Okay. So this one is actually usual noise voltage of the amplifier. So you have the EN and E tu kan? Ada kan? This one you can refer to the slide as well. New. Don't save. Tak apalah, don't save. Noise voltage of the amplifier. Which page? Yeah.
Kalau kat buku page 12 tu.
Yes. This is if it's the module is from not only page 12, but at least you know it's from page 12 lah. Okay. So if you see this one is quite doable. Okay. It's quite doable, but of course it's different scenario, because when you answer this, you actually able to open your slide and open your books. But can you imagine the real test one? Okay. You don't have that luxury. Okay, so please prepare. Okay, please answer this. Try to make exercise try to complete this exercise, and prepare for the quiz one. Okay, so okay, we finished it. I believe you have other class maybe after this. Okay, so I will share the recording later on. Okay, thank you. Assalamualaikum. See you next Sunday.
Thank you, Doctor.
Okay.
Thank you, Doctor.